when scientists observe a comet, they expect its jets to behave in a predictable way. As sunlight heats the surface, ice turns into gas and escapes through weak points, forming narrow streams that extend into space. These jets usually stay aligned with the comet's rotation and the direction of the sun, changing only gradually as the comet spins. That expectation held true for countless comets we've studied until 3I, Atlas. Instead of steady, well-behaved jets, 3I, Atlas showed motion that didn't quite settle. The jets appeared to shift, wobble, and change orientation in ways that standard models did not immediately explain. For an object that had already traveled between stars, this behavior stood out. Scientists weren't looking for something dramatic. They were looking for something familiar. And what they found was subtle but important, a reminder that even the most basic comet behavior can look different when the object comes from beyond our solar system. What made 3I Atlas stand out was not the presence of jets. Comets produce jets all the time, but how those jets behaved over time. As astronomers tracked the comet using high-resolution telescopes, they noticed that its jets were not stable. Instead of maintaining a consistent direction relative to the nucleus, the jets appeared to shift and wobble as observations continued. This kind of motion is unusual, especially when it persists across multiple observation sessions. Even more surprising was the appearance of a sun-facing structure, sometimes referred to as an anti-tail. Normally, comet tails are pushed away from the sun by solar radiation and the solar wind. In 3I Atlas's case, dust structures aligned in a way that briefly appeared to point toward the sun, a rare geometric effect that requires very specific viewing conditions and dust dynamics. The wobbling behavior suggested that the jets were being influenced by complex rotation. Rather than rotating smoothly around a single stable axis, the nucleus of 3I Atlas may be rotating in a slightly irregular way. As different active regions on its surface became exposed to sunlight, the direction and strength of the jets changed. This behavior forced scientists to reconsider early assumptions. Initial models treated the nucleus as relatively simple, but the jet motion hinted at a non-uniform interior with uneven ice distribution and multiple active vents. Such complexity is not impossible, but seeing it so clearly in an interstellar object was unexpected. What made this especially notable is that these observations were confirmed independently by different observatories. This wasn't a one-off illusion or imaging artifact. The jet wobble was real, repeatable, and measurable. In short, 3I Atlas didn't violate known comet physics, but it pushed the limits of what scientists expected from a visitor that formed around an entirely different star. Scientists do not believe the strange jet behavior of 3I Atlas is the result of anything exotic or unknown. Instead, the leading explanations are rooted firmly in well-understood comet physics, applied to an object with an unusually complex structure. The most likely cause is irregular rotation. Many comet nuclei do not spin smoothly like a balanced top. Instead, they rotate unevenly, sometimes tumbling slightly as they move through space. If 3I Atlas has an irregular shape, which is common for comets, its rotation axis may shift over time. As a result, jets originating from fixed locations on the surface would appear to wobble as the nucleus turns. Another key factor is uneven surface activity. Comets are not uniformly active across their surfaces. Some regions contain volatile ices that vaporize easily when exposed to sunlight, while others remain inactive. As 3I Atlas rotates, different active regions are illuminated, turning jets on and off or changing their intensity. This can create the appearance of jets drifting or changing direction. The comet's interstellar origin may also play a role. Having formed around another star, 3I Atlas likely experienced a different temperature history and radiation environment before entering our solar system. This could have led to unusual layering of ices or fractures within the nucleus, producing jet activity that is less symmetrical than what scientists typically observe in solar system comets. Additionally, interactions with the solar wind can subtly influence how gas and dust flow away from the nucleus. While this does not create jets, it can affect their shape and visibility, enhancing apparent motion when combined with rotation. Taken together, these factors provide a coherent explanation. Nothing about 3I Atlas breaks the laws of physics, but its behavior reflects a more complex internal structure than scientists initially assumed, reminding us that comets from other star systems can still surprise us. What made the behavior of 3I Atlas so striking is not that it was impossible, but that it challenged expectations formed from very limited experience. Until recently, scientists had only observed a handful of interstellar objects. Based on those few examples, it was reasonable to assume that most interstellar comets would behave similarly to comets from our own solar system. That assumption turned out to be incomplete. Researchers expected 3I Atlas's jets to follow familiar patterns, steady outgassing, gradual changes tied to rotation, and structures that could be modeled with relatively simple assumptions. Instead, the jet motion was more dynamic and complex than anticipated. The wobbling behavior suggested that the nucleus was not just active, but internally varied in a way that early models didn't fully capture. This wasn't expected because scientists simply don't have a large sample size. With so few interstellar visitors observed, every new one carries the risk of overturning assumptions. 3I Atlas showed that even basic comet behavior can look different when the object formed under completely different conditions around another star. And that is exactly why this matters. Understanding how jets form and evolve is not just about describing a single comet. Jets influence a comet's motion, its rotation, and even its long-term survival. They affect how scientists estimate mass composition and internal structure. If jet behavior varies more widely than expected, models must be refined not just for interstellar comets, but for comets in general. More importantly, 3I Atlas serves as a preview. As detection technology improves, interstellar objects will become more common discoveries. Each one will arrive unannounced, move quickly, and offer only a brief window for study. 3I Atlas reminds us that the universe is more diverse than our assumptions, and that every visitor from beyond our solar system has the potential to teach us something new.